Sir?
Yes.
Yes, sir. I also had the same question. Like, I was confused in the part where we use mean value theorem. Like how did we use that? So, sir, can you explain
Hmm.
that part also?
Yeah. So did you see the notes?
Yes, sir.
All right. Okay. Can you see my screen?
Uh, yes, sir.
So let's go back. Uh, this was the last part, right? Yeah. Hmm. So this was the example, the first one, first question. See, f and x is you look at n plus x, right? Now, does this converge even pointwise?
No, sir.
This does not converge, but derivative is always one for all n, right? This is actually true for all n, right? The derivative is always one,
Yes, sir.
so it converges uniformly, right? Right. So derivative converges does not imply that function converges.
Yes, but if function is pointwise, then derivative, uniform convergence of derivative implies uniform convergence of the function.
Ah, right, right. I mean, it might happen that function may not even converge. But even if the function converges at one point, then it will converge everywhere.
Oh yes, because the derivative converges uniformly. So I mean, if it converges at one point, you can always from these maybe affine approximations to show that the function converges at all points.
Well, yes. So that was using mean value theorem. You prove that converges absolutely uniformly actually. All right.
Yes, sir.
So this is the first one. So is this clear now?
Okay, sir. I just want to look again at the proof one time.
Proof of what?
Proof of this that if the function converges pointwise, and the uniform convergence of derivative implies the uniform convergence of the function.
Yeah. So that's what the other person who was that asked, right?
Yes, sir.
Yeah, what is your name?
Ayush.
Ayush. Okay. Yeah. So where did I give that proof? Here. So what you want to show is that Fn is uniformly Cauchy, right?
Yes, sir.
So now you look at Fn minus Fm, then you add and subtract with Fnt and Fmt. Fnt minus Fmt you add and subtract, right? Right, is this fine? So this is
Yes,
nothing
sir.
else
Yes, sir.
addition and subtraction. So now you look at Fn minus Fm, that function. Fn minus Fm. So you here what you need to consider is as follows. You consider
Sir,
this one. Yes?
I was confused in this part. Like,
Like,
uh,
mean value theorem on what?
yes, sir. To
Okay.
use mean value theorem, the
Uh,
function both have to be the same, right? Fn x minus Fn t.
of course. So use mean
Like,
value theorem on this function. Consider the g equal to this.
okay,
Okay? So
yes,
what is this? This one is g of x, right?
yes, sir.
Minus g of, this one is g of t,
Yes,
right?
sir. Yes,
All
sir.
right. So now you can use, and
Okay.
this one is g prime. Uh, this one is g prime at x naught. Is this fine now?
Yes, sir. Yes, sir.
Yeah. So you have to use not on fn or fm individually, but the difference.
Yes, sir.
All right.
I think I missed that part in my notes.
Oh no, no, I have sent this note also, so you could have looked at this.
Yes, sir. Yes. Thank you, sir.
Yeah. Any other question here? This is interesting, na? So this function, if the derivative converge, function might not converge, but if it converge at one point, it will converge everywhere. Right? See here, and why one point is important? Because here you are considering just one point, right? You can take any point here, just one point if it converges. So this part is at automatically is clear, right? Because derivative converges uniformly. This part we know. Only problem part is this one. But this one is we need uniformly Cauchy for Fn at one point. Just the point T, nothing else, nowhere else. Is this clear? See here, this is a fixed point. This is a fixed point. This is a fixed point. T is a fixed point, and so we need the convergence of this part, Fn, convergence of Fn or uniformly Cauchy of Fn at the point T. Other term comes in terms of derivative. Do you see the point? Why you need only one convergence at one point only to get the uniformly convergent, the uniform convergence. Is this clear? See
Yes,
this
sir.
part, you need only convergence at one point. So uniformly Cauchy at one point. And this part comes from derivative. All right? So
Yes,
one
sir.
point
Right, sir.
implies, so hence the remark here. We just need one point only. Okay? Any other question here? So in this case here, we can actually relax assumption a little bit. See here, we consider uniform convergence on this one, right? And we considered bounded interval. Actually, we do not need that. See, you can allow infinity as well. You can allow infinity as well here. Yeah, maybe I should. Maybe I should write write separately the new version. So today is 23rd. So theorem. So this one only, but we actually will relax the assumption a bit here. Suppose Fn is a sequence of differentiable functions on AB. Now infinity minus infinity all are allowed. Sequence of differentiable functions on AB such that the following order. Such that for every alpha, beta in R, A less than alpha less than beta less than B, the following holds. B Fn converges to F pointwise also here this one we need later. So pointwise on AB and Fn prime converges converges uniformly on every closed interval alpha comma beta that lies in AB. Is this part clear? Fn prime converges uniformly on every closed interval alpha beta which lies in this. Now A and B can be infinity or minus infinity, right? So here we needed uniform convergence on whole interval, and that is the reason we need a bounded one. Otherwise there will be a problem. And then F is differentiable. Conclusion is same. And F prime x is limit n tends to infinity fn prime x for all x in AB. Is the statement clear? The important point is this is on every closed interval. It's not just one closed interval. Rather, every closed interval you have this. Is this fine?
So in the previous theorem, the statement was that that f dash n converges on the open interval AB. Okay.
So this is very restrictive. So A and B here we needed bounded one, right? But in this case we allowed A and B to be minus infinity or plus infinity both. So you can function can be defined on whole of R. Right? So that was a restriction. And you converge in yes.
So the second theorem is the stronger version.
Second?
The second theorem is stronger than the first one.
Right. Second theorem is much stronger, because you can apply on certain cases where this theorem may not be applied because of this reason. You need boundedness and stuff. But here the function is whole of R. And actually the proof is same. There's nothing difference in the proofs. That's why I actually incorporated this one, which is stronger. So here on every closed interval means this one, every closed interval means that it converges uniformly on every compact subset. Right? Is this clear? That this converges, prime converges uniformly on every compact subset. Right? You take compact subsets of open interval AB. Is this clear?
Yes, sir.
Yeah, because any compact subset is contained in a closed interval. Hence, it will converge uniformly. All right, so let's come to the proof of it. Proof is not very difficult. Okay, so what do you want to show? You want to show f is differentiable. So what do we need to show? Fix a point x naught AB, and we want to show well, this fix a point come inside the proof, not in the statement. So fix a point x naught in AB. Right? You just choose a point. Yeah, choosing would be better. But to show limit x tends to x naught, f of x minus f of x naught by x minus x naught exists. right? We want to show this. Okay. All right. Since it converges pointwise, we know this f, and we want to show this one for every x naught, right? For every x naught in AB. Okay. And define phi n, uh, phi x, let's say, phi x, fx minus fx naught by x minus x naught, right? For x is in AB minus the point x naught. All right, this is perfectly defined. This is continuous, right? On this AB minus x naught. And we also define phi n x, uh, phi n from open interval AB to R by phi n x fn x minus fn x naught by x minus x naught, and x is not equal to x naught, and fn prime x naught for x equal to x naught, right? Is this clear? This is our old friend. We have used this one before, right? While doing chain rule, we actually did this. Now phi n is continuous on AB, right? Is this clear? So I should put the reason, since Fn is differentiable, right? So limit as x tends to x naught, this one exists because Fn is differentiable, and the limit is Fn prime x naught. So phi n is continuous. All right. And does the sequence phi n converge? Any guess? Yeah, does the sequence phi n converge?
Yes, it should converge.
It should converge. Can you give me a reason?
Because the function is itself converged pointwise. So if we write phi n minus phi, that mod just becomes a mod of differences of fn minus f. And we know that fn.
So at least this, for x not equal to x naught, you can take this limit and this limit, right? 1 over x minus x naught, there is no n. there,
Yes.
right? So here for x not equal to x naught, phi n x converges to phi x, right? We're looking at pointwise convergence, right? So this is pointwise convergence. Now, and of course for x equal to x naught, fn prime x naught converges, right?
Yes, sir.
That is phi n x naught. This sequence converges, right? So phi n converges pointwise. We don't know at what point at x naught what will it converge to, right? So phi n converges pointwise, that much we know. And for x not equal to x naught, we know phi n converges to phi also, right? At
Yes, sir.
x naught, where it converges, that we don't know, right? At x naught, this phi n converges, that part also we know. That will be some number. But what that number will be, that we don't know. Here, for example,
Sir,
what
at
we
x
know,
naught it converges uniformly because fn prime converges uniformly on every closed interval.
this
So,
is only one point, right? X
okay.
naught is a fixed point. So these are sequence of numbers,
Oh,
right? This converges. The question is whether phi n x converges uniformly. That is the question. That answers. If yes, then we get the answer. Do you know how? So phi n converges pointwise, right? This is clear to everybody. Phi n converges pointwise because at x naught equal to x naught, phi n x converges to phi x, and at x equal to x naught, we know derivative converges uniformly. Hence, it converges pointwise also. So at x naught, fn prime x naught will converge, which
Yes.
means phi n x naught will converge. So therefore, phi n is phi n x is convergent. So phi n is convergent pointwise on AB, right? Now, if we can prove that phi n converges uniformly,
So
then what happens?
can we show it like this? Like we already know that the derivative of fn converges uniformly. So
Yeah,
from previous theorem, we can show that the function fn also converges uniformly,
right.
closed interval. And given that fn converges uniformly, I guess we can show that phi n also converges uniformly.
Yeah, suppose it converges uniformly, then what can you say?
So then basically fnx minus fx, this doesn't depend, I mean this is less than some n of some less than epsilon when n is greater than some capital N. But capital N
Oh no
doesn't.
no. Let's look at let's not go into this complicated I mean expression. Let's look at it in simple English. So phi n is a sequence of continuous functions, right?
Yes, sir.
And suppose phi n converges uniformly. So what will be the limit function? Yeah, so we look at, so see phi n fn x naught fn
Phi
prime x
x,
naught.
right?
Yeah.
Uh, the limit should be phi x, like if it converges uniformly.
Oh no no. It converges to phi x for x naught equal to x naught. We don't know what happens at x naught, right? Assume that phi n converges uniformly,
Yes.
and phi n is continuous for every n. So what the limit function will be? Will it be continuous?
It should be f prime n of x, right?
No, no, no. I mean, there is no f prime and fn prime x at here. This is only fn prime x naught here at this point, right? My question is the following. Let me write it. So this actually would answer. So this is a digression. So suppose uh, maybe not digression, but yeah, different way of writing the proof. Suppose phi n converges uniformly. So there will be some limit function, right? So phi n, let's say phi n converges to G. So what will be G? So is G continuous?
Yeah, it should be.
Yeah, because uniform limit of continuous function is continuous. Right? Converges uniformly where? On alpha beta such that x naught belongs to open interval alpha beta. X naught is an interior point. We can make always that. Right? So G will be continuous. Then G is continuous, right? Now we know this, it converges to some function, right? Yeah? What do you know? We know it converges pointwise to phi when x not equal to x naught. Right? So G, this limit will be equal to phi for x not equal to x naught. Right? But the continuity of G would give you the limit. So this continuity of G will give you limit x tends to x naught px exists, right? Is this clear?
Yes, sir.
And this is what we need to prove, right? Right?
Yes, sir.
So the only thing is to show is that phi n converges uniformly. So the only thing is to show so maybe yeah we can incorporate in the proof itself. So that will prove the theorem. Will prove the theorem. Right? So what is remaining is what remains to prove is phi n converges uniformly on every closed interval alpha beta in AB. Right? Is this clear? That we only need to prove that phi n converges uniformly? Hmm?
Yes, sir.
All right. Now this is the old trick, uh, using mean value theorem, right? So one person was already saying that, right? So fix a closed interval alpha beta such that x naught is inside. All right. Now we will show that Pn is uniformly Cauchy. All right. A simple, the old trick. There's nothing here, nothing new. So Pn x minus Pm x this equal to Fn for, so we do it for x not equal to x naught. For x equal to x naught, we know it is uniformly Cauchy. It is Cauchy. The sequence is Cauchy. So now only we need to look at this one. X naught, x minus x naught minus Fm x minus Fm x naught by x minus x naught. So this one you get it here. Fn x. So you just subtract minus Fm x minus Fn x naught plus Fm x naught by x minus x naught. Is this clear? Yeah. Now this one, this is Fn minus Fm at x minus Fn minus Fm x naught. So to make things easier, I wrote this trick before, right? In the context of uniform convergence, pointwise to uniform by x minus x naught. I use mean value theorem. So there exists C in the interval x comma x naught or x naught comma x, depending on which side x is. Fn x minus x naught times fn minus fm prime at c by x minus x naught. Right, so this gets cancelled. So this is mod fn prime c minus fm prime c. Right? Now look at, consider this to be 1, and now use the following. Since fn prime converges uniformly on alpha beta for every epsilon there exists n naught belongs to the natural number such that mod of fn prime x minus fm prime x less than epsilon for all n mn mn bigger than n naught, and for all x belongs to closed interval alpha comma beta. Is this clear? Is the argument clear? This is not a new argument. This is old argument. We have already seen it. Is it fine? Now, from 1, we get that. So this worked for C, this C only. The C was any point, right? So we don't know what point. So mean value theorem gives an existence. It does not give the precise C, right? So that's why we need uniform convergence. All right. So now this gives you phi and this one. Phi n x minus phi m x, which is equal to, yeah, we did not need in triangle inequality this time. Fn prime c minus fm prime c, which is less than epsilon for all mn greater than n naught, right? Hence, and now this statement is true for all x in alpha beta, even for x naught also. So yeah, this is true for x minus alpha beta minus x naught and phi prime phi n x naught minus phi m x naught. This is equal to fn prime x naught minus fm prime x naught, which is also less than epsilon for all mn bigger than n naught. This is also by this one. I call this 2 from 1 and 2. Right? So this implies for every epsilon there exists n naught such that phi n x minus phi m x less than epsilon for all n bigger mn bigger than n naught, and for all x belongs to closed interval alpha beta. So this implies phi n is uniformly Cauchy. This implies phi n is on alpha beta. This implies phi n is uniformly convergent on closed interval here. Alpha beta. Right. Now we proved phi n to be uniformly convergent. Now we come here, right? So this limit exists. So call this star. Star tells us, gives us that limit x tends to x naught phi x exists, that is limit x tends to x naught fx minus fx naught by x minus x naught exists, right? So this implies f is differentiable at x naught since x naught was chosen arbitrarily. Since x naught was chosen arbitrarily, f is differentiable on the open interval AB, right? And now what is f prime x? F prime x, which is this one, limit x tends to x naught phi of x, which is limit x tends to x naught and then limit n tends to infinity phi n x. All right.
So isn't that f prime of x now?
Yeah, that is true. That is true. So we are coming towards that. So now here, this one, well, this right. So this one is actually this is continuous. So this was the limit, right? So limit gx naught. So this was continuous. So you can actually, so what we proved is this one, limit x tends to x naught, Pn x. So this one limit n tends to infinity Fn prime x naught. So Pn x naught. So what is this? This was limit n tends to infinity Pn at x naught, right? This was it, isn't it? Since the limit of Pn is continuous. So because of this reason, we can interchange limit here. So interchanging limit is very important concept. So be clear. Here we had this one. Because we had this one, that implies here this interchange. This interchange. Is this clear?
So in the first line you've written f prime of x. Shouldn't it be f prime of x now?
Ah, sure. Yeah, that is true. Thanks. Yeah, this is a prime of x naught. Yeah. Yeah, x naught was chosen arbitrarily, so one can actually write it uh, since x naught was chosen arbitrarily. F prime x is limit n tends to infinity Fn prime x. All right. Any other question here?
Sir,
Yes.
can you re-explain the limit exchanging part?
Is this true here?
Uh, yes, sir.
Yeah, that's what it is. So if you see here, this line gives you this one, right?
Yes, sir.
Because phi x is limit of phi n,
Yes, sir.
right?
Yes, sir.
All right. And this line is actually gives you this, because n tends to infinity phi n x naught is phi n is continuous. So this is this,
Yes, sir. Yes.
right? So this is, I mean, two limits together. It might look scary, but it is actually coming from here.
Okay, sir.
And
Okay,
yeah,
sir.
what is
Understood.
important is to understand how and when one can interchange the limit. Two limits here actually. So here we can interchange the limit and the derivative. Derivative is a limit again. So that's what it is. That's why you get two limits here. So interchanging two limits, interchanging summation with the limit. So those things we'll talk about. So now this is for sequence. Now one can try this theorem with a series. You'll get interesting result. Yeah.
So you mentioned something about the continuity of the function allowing us to interchange the limits. Could you repeat that?
Continuity of the function phi n x and the and uniform convergence of phi n x, that gives you continuous limit, right? So what I wrote here as g, right? Somewhere I wrote, yeah, g, right? So g is continuous. So that gives you this limit exists, right?
Yes, yes, sir.
And what is this? This is,
F
yeah,
dash Yeah.
Right. So now this phi n converges to G. So here, so this should be G of x naught, right? G of x naught, right? This limit exists, and this should be this G of x naught.
Yes, sir.
So that means which is limit n tends to infinity phi n of x naught, right?
Yes, sir.
So which is limit n tends to infinity fn prime at x naught, right?
Yes, sir.
Right. So that's what we got here. That's why we got here this one, this limit, right? Fn prime x naught, right? The other part is the already interchanged limit. Yeah. So whatever I wrote here, we explained it that there. So this limit exists, but this is one viewpoint. Other viewpoint is this is limit n tends to infinity phi n x, right? So you see this limit, then this limit, and here it comes first this limit and then limit x tends to x naught, right? Because phi n is continuous, so this limit actually gives you phi n x naught. So all it actually, the main point here to show this limit is continuous, which in other words gives you comes from that phi n converges uniformly. So the continuity of the limit gives all this, right? Is this clear now? Or any other question? Okay, so since there is no other question, so we'll meet you. I mean, we'll meet again tomorrow. Okay.